So the focal point of this learning module is Nmr Spectroscopy. Nmr Spectroscopy is an example of an absorption spectroscopy. But let's break down these the acronym once more. So NMR is nuclear magnetic resonance. Now, nuclear we've been talking about a bit. This refers to the nucleus of an atom. And if you recall, we had talked about how there were certain nuclei that we can look at, like 1H, the 1H nucleus and the C13 nucleus, but and 19F, 31P, that sort of thing. But then like carbon 12 we can't look at efficiently. Nitrogen 14 we can't look at. So it's a particular nucleus of an atom. Now magnetic refers to, just if I'm a little bit colloquial here, a huge magnet's involved. And then resonance refers to the absorption event. That is resonance, or maybe resonant, excuse me. Resonant absorption is involved. Okay, so those are the letters. Now, as I mentioned, this is very similar, NMR is, to MRI. In fact, incredibly similar. It's basically the same technique, except one's engineered for people and the other one's engineered for samples of molecules. So what we see in what MRI stands for is magnetic resonance imaging. Once again, we have magnetic, which refers to huge magnets involved. Resonance refers to resonance absorption. Now, we're not looking at various nuclei. We're looking at one particular nucleus, which is the hydrogen 1, the 1H atom, within water molecules, creating images useful for understanding various things, for the most part, medical conditions. But I mean, there's fMRI, which is used to study things that are happening inside the brain. But anyway, it's an imaging technique, as opposed to looking at a variety of nuclei and trying to get the chemical environment from that, which can then give you the structure of a molecule. Okay, so let's break down the nucleus. Once again, we've done this in Organic Chemistry 1, but let's recall the nucleus has protons and neutrons. Based on how we've labeled NMR, nuclear magnetic resonance, it seems like the electrons aren't necessarily involved too much, and they influence everything about the chemical environment. And so their presence is sort of inferred from our studies of the nucleus using NMR technology. Now, these are the two players then. And in particular, we want to focus on the protons, because protons are always present inside of a nucleus. Protons are, first of all, massive. I know one AMU is not that big compared to me, but that is the mass of a proton, but that's because I'm composed of so many protons. So protons are indeed massive, definitely compared to the electrons, and they're also charged. So let's think about the proton. So if we wanted to draw a proton, it's kind of helpful to draw a proton as a sphere. Now this sphere, as it exists in the universe, whether it's within the nucleus of an atom or a single hydrogen atom floating around, is for the most part doing the same thing. That is, it's not generally influenced by the frictional forces that you and I experience. And so this particle actually is spinning. So it actually spins. So I don't really know how to draw that. Maybe I'll put a plus and then have some curly arrows. So this thing's kind of spinning around. Now, that's an important feature. Not only is the proton positively charged, not only is it massive, but it's also spinning. And that's an important thing to note, because in physics 2, I remember learning, I don't remember understanding exactly why this all occurs, but I remember learning a critical feature of the universe is that things with charge that are in motion create a magnetic field. So things with electronic charge that are in motion create an electronic field. And so what's happening then is our proton, our positively charged billiard ball that is rotating, is creating a magnetic field. It's, well, creating is a weird word for this. It's emitting a magnetic field. And the magnetic field actually creates what's called magnetic field lines. These look like Dumbo ears, and they try to be as much as possible perpendicular to the vector of motion. So if we're spinning horizontally, these lines like to move vertically up and down, but they're going to try to connect with each other. And you get this magnetic field that forms, and there's various lines that can be predicted using very complicated physics. I'm just drawing these haphazardly. It would be a bit symmetric. All right, that's a complicated picture, but these magnetic field lines are important to consider for understanding NMR. You know what, though? Let's just, for the sake of simplicity, think about this as equivalent to a run-of-the-mill sort of bar magnet. That is just a magnet that you could play with as a kid, or I don't know. I feel like I did. Maybe kids these days, at least my kids, have more interesting toys. Anyway, a magnetic field has kind of two sides. One is labeled plus and minus. These are just the magnetic poles. Don't relate the plus and the minus to a charge. Rather, this is just the magnetic poles. If we wanted to, we could draw electronic field lines, much like those seen in our proton that's spinning. So my point is that when the proton, with its mass and its charge, starts to spin, it's going to emit magnetic field lines in the same way that a bar magnet would. So this is a useful analogy. Okay, now the positive and the minus, again, are just the magnetic poles. Okay, where, you know, if you put two plus ends together, they're going to repel. A plus and a minus end, they will be attracted to each other. Okay, so what I want to do then is I want to do an experiment where we take a test tube. Now we're getting back into the chemistry realm, right? So we have a test tube, poorly drawn test tube, and I'm going to sprinkle in some atoms. Okay, now these atoms are going to have nuclei, and in these nuclei we're going to have protons. And so these protons, like I said, are going to spin, and if things with charge spin, they will emit magnetic fields. I should be careful. They're going to emit magnetic fields, and they can be thought of as a bar magnet. So instead of drawing a bunch of little things in this test tube that have chemical structures like bond line structures with double bonds, single bonds, all that sort of thing, I'm going to consider maybe they're just a bunch of little bar magnets. And they're strewn about, floating around, doing their thing. But for the most part, they're bar magnets, and some of them might be sideways, and some of them might be upside down. Okay, now what I want to do is to this system, I want to apply a very large magnet, a huge magnetic field, that is. I'm going to introduce like a superconducting magnet that emits a gigantic magnetic field. So add a very large magnetic field. Okay. I'm going to make my test tube wider. The test tube didn't get wider by the magnetic field. What I'm going to do is just, I'll pick a different color here. Let's pick something a little gentler, like this pink color. Okay, so this is my external magnetic field. So again, we put this in the presence of a gigantic bar magnet that emits a huge magnetic field. Okay, what's going to happen then? Well, all of these little tiny bar magnets are going to feel the presence of that gigantic magnetic field, and start to flip. How are they going to flip? They're going to flip such that they're all aligned with the magnetic field. All right, I'm going to go ahead and just add a few more bar magnets. 4 just is kind of a bummer number. So they're all going to flip so that they're facing vertically, okay? Now, they're going to face vertically, but the interesting thing is that we don't have to worry about the external, at this point, well, I won't even say. Okay, they're going to flip such that about, let's see, I've got 6 here. Roughly half of the bar magnets are going to be positioned such that the plus side of the plus magnetic pole of our bar magnet is facing up. And the other half are going to have the minus bar magnet facing up. Now, what is interesting about that is that's very predictable. Statistically speaking, that's very predictable. And if you imagine when we put atoms in, we don't just put 4 or 6 atoms into our system, we put trillions upon trillions of atoms. So the statistical 50-50 ratio is very, very predictable, even if the big magnetic field has itself a plus magnetic pole that's really big and a minus magnetic pole that's really big. So the way I have this depicted in this particular instance, the negative magnetic pole is kind of down and the positive is facing up. Okay, so what we say then is there's a few observations to make about this situation. Number one, let's just set this up a little bit better. After introducing the large magnet, okay, put a star next to this, 1/2 are aligned with the big magnet. I'm running out of space. And 1/2 are opposing the big magnet. Okay, so 1/2 are aligned with and 1/2 are aligned against. Let's visualize that a little better. So let's say being aligned with. And again, this is 50% of the atom population. So we've put a bunch of atoms in, and I'm saying that 1/2 of our atoms are aligned with the magnetic field. Now, what that looks like is that we're going to have the plus up and the plus and the minus down, because in the case of the way I had this depicted, we had the positive magnetic pole up and the negative magnetic pole down. So 1/2 are aligned with and 1/2 are opposed. Now I realize that if you haven't had physics, maybe you want a lot more explanations about a lot of this. And, I would really encourage us to remember that we have a lot of opportunity to learn all of this in other contexts. Right now, we're trying to understand what's happening in NMR spectroscopy. So, unfortunately, we just have to kind of accept at this stage in the game that spinning charges create magnetic fields. And if you put those in the presence of a large magnetic field, for some reason, not all of them align, okay? Instead, 1/2 aligned with and 1/2 are aligned against. Being aligned against. And again, this is 50% of the population. So it's very predictable. I mean, it might be such that, and 50 is like pretty rough. It actually might be a little bit more, a slight favoring towards being aligned with the external magnetic field, but it's very close to 50-50. Okay, which is helpful for us. Because what this tells us, this is the situation we're set up in. We haven't done any spectroscopy. We haven't really introduced any radiation. We've just put everything into the presence of a magnetic field that's really big, much bigger than the magnetic field emitted by the proton within the nucleus. Now, what's great about this is when we introduce that magnetic field, that huge magnetic field, and only when we introduce that magnetic field, there are now two states a nucleus can be in when it's exposed to an external magnetic field. Okay, we put everything in the presence of the magnetic field. They all align vertically, but there's now two states. The two states are aligned with and aligned against, kind of depending upon the position of the various magnetic poles in our external magnet. Now, what's cool about this is the aligned with state is lower in energy, and we could call this our ground state. The aligned against is higher in energy. And so if it's higher in energy relative to our aligned with state, we could call this an excited state. That's a great way to think about what's happening. Okay, so what we do is we can kind of more formally label these things. The aligned with state, which is lower in energy and considered to be the ground state, this is called the alpha state. And the aligned against is the beta state. Not super creative, alpha being first, beta being second, I guess. Okay. So we have these two states. One is considered to be a lower energy ground state. The other one is a higher energy excited state. Now, the other thing I want to just mention is that we call the large external magnetic field, we call that H0. So I'm going to have the alpha state, the beta state, and H0 going forward as we talk about Nmr spectroscopy. And there's the letters for alpha and beta. We've seen those before in some contexts. Okay. So that's sort of the setup for our absorption spectroscopy technique. And maybe you can see what's happening here, but in NMR, and MRI for that matter, we use absorption spectroscopy to measure the energy between the alpha and the beta states. The energy difference between the alpha and beta states. I better write and here. Now, more specifically, what the chemical reaction looks like is we consider our bar magnet first in the alpha state, which for my pictures that I was providing earlier, that would have the positive magnetic pole facing up to match that magnetic field from H0. Now we're going to supply some energy to the system, and that energy is a photon. And we're going to flip that alpha state to a beta state. Flip that to a high energy system. Okay. So this is alpha state is our ground state. The beta state is our excited state. And our energy comes from a photon. And what's cool about this photon is if we calculate h nu, take Planck's constant times the frequency of the light that's required to do this particular excitation event, that's required for this particular absorption to occur, we get something that's in the range of a radio wave. It kind of varies depending on what we call the chemical environment of the nucleus that we're looking at in particular. But for the most part, to flip these bar magnets over, to flip them on their heads, for example, requires only a radio wave. This is a very inert, innocuous, harmless wave that we're experiencing all the time. And it's just not a big deal. This is great because before MRI came along to image inside the body, we would have to rely on X-rays, which are much more harmful and complicated. And what else? Or we'd have to rely on surgery. So what we have to do then is take people and put them into big magnets so that we can observe the flipping of the water molecules. And big magnets are really scary if you're like a robot or a computer device. But for the most part, unless you have something like a pacemaker or something else like that inside of you, you could just sit and chill out in a magnetic field all day, and it's not a big deal for us biological organisms. Flipping all of our nuclei on their heads doesn't cause detrimental effects as much as I'm aware, which there have been extensive studies into this. Okay, so that is sort of the setup for what happens in NMR spectroscopy. The next few things are going to be more of the details for a particular NMR experiment. I think it seems appropriate to save those for another video. So I'm going to cut us